In the Bronsted-Lowry concept, acids and bases, acid-base reactions are viewed as proton transfer reactions. The stronger the acid, the weaker the conjugate base. In what ways are redox reactions analogous? Okay, so acid-base reactions are proton transfer reactions, right? The acid's donating the H+, the base is accepting the H+. Redox reactions are electron transfer reactions, where something is losing electrons, being oxidized, and something is gaining electrons, being reduced. Equilibrium lies to the side of the weaker oxidizing agent. Okay. So if you're something that doesn't want to give up electrons, I mean, this is why silver is so good for jewelry. It's hard to get the electrons off. But if you manage to get the electrons off of silver to make silver ion, you've made a very significant oxidizing agent. It wants the electrons back. So strong, in fact, that if you get silver ion close to copper, the silver ion will lift the electron off of the copper to make copper 2+ and reproduce the silver. So this would be a very spontaneous reaction. Silver plus taking electrons away from copper, and that's how it works. So if you don't want to give up an H, you make a significant base. If you don't want to give up electrons, you've made a significant oxidizing agent. The diagram that follows represents a molecular view of the process occurring at an electrode in a voltaic cell. Okay, so we've got atoms being pulled out of the crystal. Does the process represent oxidation or reduction? All right, so I'm looking at these balls. They're getting smaller. All right, so you're taking something away from them. So this is oxidation. B, is the electrode the anode or the cathode? Well, oxidation occurs at the anode. All right, so we've got some metal, right, metal crystal, where the electrons are being taken off of the metal atoms to form cations. Why are the atoms in the electrode represented as larger spheres? Those are the atoms with their electrons, and they've lost their outer electrons, their valence electrons, and shrunk. So this is the picture, right? Take the outer electron, the 4s electron away from potassium, and you've lost that 4s shell. You're just left with a core, and you get a real shrinkage when you compare the potassium cation to the potassium metal. For a spontaneous reaction, A reacting with B to make A- and B+, answer the following questions. A, if you made a voltaic cell out of this reaction, what half reaction would be recurring at the cathode, and what half reaction would be recurring at the anode? All right. Oxidation occurs at the anode, right? Oxidation is a loss of electrons. So since B is going from B to B+, it's losing electrons. And since A is going from neutral to A-, it's gaining electrons, being reduced. So reduction occurs at the cathode, A taking an electron to become A-, and oxidation occurs at the anode. All right. B, which half reaction from A is a higher potential energy? All right, so if this is a spontaneous reaction, we're lowering potential energy. So it must be that you have a more unstable state with having A separated from B. So you're starting at a higher potential energy at the anode. All right, so the anode is a more unstable condition, and the electrons are taken to get to a more stable condition. C, it'd be positive. The voltage for the cell would be positive if this were a spontaneous reaction. All right, so positive voltage at standard conditions means that if you completely convert reactants into products, you'd be releasing electrical energy, right? So you'd have a positive voltage for the cell. Consider the following table of standard electrode potentials for a series of hypothetical reactions in aqueous solution. All right, so they're giving us these, made up reductions, right? So gaining electrons and turning into something generates a current. So a voltage, I should say. Which substance is the strongest oxidizing agent? All right, so the oxidizing agent is reduced. So the way you measure how strong the oxidizing agent is by how positive the voltage is, all right, the reduction potential. So the strongest one would be A, all right, it has the most positive voltage, best oxidizing agent. Which substance is the weakest, all right? So the one with the least positive, right, the most negative would be the worst oxidizing agent. Now, that's the thing. If D3 plus taking 3 electrons turning into D is a poor oxidizing agent, that means that D is really easy to take electrons off of. So if I turn it around, D solid turning into 3 plus by taking 3 electrons off, this means that it's a good reducing agent. It's easily oxidized. So it's going to have a very large oxidizing potential. So turn the reduction half reaction around and you've got an oxidation half reaction. And the voltage for this oxidation is same magnitude but opposite sign. So this is how we get an oxidation potential. Turn a reduction potential around and just change the sign on it. Nice to live in a predictable universe. Which substance can oxidize C2 plus from here, right? The ones that are above it, right? So B2 plus can take electrons away from C2 plus, and A plus can take electrons away from C2 plus. So if I wanted to get the voltage generated by this reaction, I would turn the reduction potential for C2 plus around, make it an oxidation potential, add to the reduction potential for A plus and B2 plus to get how much voltage is generated by the reaction. It's standard conditions. Consider a reaction for which the voltage at standard conditions has a negative number. A, what is the sign on delta G naught for the reaction? All right, so if you have a voltage at standard conditions, that means 1 molar concentrations of the reactants and the products. This implies a non-spontaneous reaction. So there's a relationship between E naught and G naught, right? So if I plug this in with the number of moles of electrons being transferred and times Faraday's constant, I would convert to G naught. And if I have a negative value for E naught, negative times a negative gives me a positive. So a positive G naught value means a non-spontaneous reaction. Right, so this reaction stops with a lot of reactants left over, very few products made. So you're going to have a K value smaller than 1, that's B. So there's a relationship between the voltage change at standard conditions and K. Right, so I know the number of moles of electron transfers, that's N, divided into the constant for Faraday, times the log of K. We can convert from K to E naught, and we can rearrange and solve for K. There's also a relationship between the voltage at non-standard conditions and the voltage at standard conditions. So in this situation, we're talking about Q, right? Products over reactants raise their stoichiometric coefficient. So at the beginning of the reaction, this reaction will slide forward a little bit, right, until the concentration of the products is such that the reverse reaction stops it. So to answer C, can the electrochemical cell based on this reaction accomplish work on its surroundings? My answer is yes. At the beginning of the reaction it can, but the reaction stops. And when the reaction stops, right, we get a voltage of non-standard conditions of 0. It means you're at equilibrium. So this will happen pretty quick for a non-spontaneous reaction. Again, Q is products over reactants raise their stoichiometric coefficient. So if I have a no products basically and all reactants, this thing will probably slide forward and generate some positive voltage at non-standard conditions before it stops. Considering the following voltaic cell, all right, so we've got iron losing electrons. They have the electrons going over to the silver side, being gained by silver plus. So the cathode is where reduction occurs, all right? So red cat, reduction occurs at the cathode. So this is where silver plus is taking electrons, becomes silver metal. There we are, red cat. The cathode is where reduction occurs. I don't like a lot of little sayings, but this one always stuck with me. So, red cat, reduction occurs at the cathode. B, how would you determine the standard voltage generated by the cell? All right, so we go to a reduction potential table, right? Gives us the voltages at standard conditions for the different oxidizing agents. And we look up what the reduction potential is for silver. And we look up what the reduction potential is for iron, and we can figure out what the voltage of the cell is. Now, since silver plus is higher on the chart than iron 2 plus, it means, yeah, this is going to be a spontaneous process. We're going to generate a positive voltage when silver plus takes electrons away from iron to form iron 2 plus. So I look up the reduction potentials for silver plus and iron 2 plus, recognizing that it's silver plus taking electrons away from iron. So if I turn the reduction potential around, right, turn it into iron losing electrons, become iron 2 plus, I change the sign on the reduction potential and it becomes an oxidation potential. So when I add these two potentials together, let's balance the equation, right, in terms of electrons being transferred, right? 2 moles of electrons have to go into the reaction in order for 2 moles of electrons to come out, right, being lost by the iron. Notice when I multiply the half reaction by 2, right, to get the right number of electrons going in as coming out, it doesn't have an effect on the voltage. So it's not like delta H, where whatever you did to the half reaction or did to the reaction, you did to the delta H, right? So this doesn't affect the voltage, all right, balancing this. So when I add these two potentials together, the oxidation potential to the reduction potential, I get the voltage for the cell. How much voltage will be generated at standard conditions, right? 1 molar concentration of the iron 2, 1 molar concentration of the silver. All right. What is the change in the cell voltage when the ion concentrations in the cathode half cell are increased by a factor of 10? All right. So the Nernst equation equates voltage at non-standard conditions to voltage at standard conditions, right? I subtract this term, right? This constant divided by the number of moles of electrons being transferred times the log of Q, right? Products over reactants raise their stoichiometric coefficients. So just as with G naught, right? G naught was used to figure out what the magnitude of K is. It's the same with E naught, right? I can use E naught to find the magnitude of the equilibrium constant. And just like with G absolute, right, G at non-standard conditions, I can use the voltage at non-standard conditions to figure out where I am in terms of equilibrium. Am I at equilibrium, past equilibrium, or before equilibrium? All right, so with 1 molar concentrations, right, if I plug this into the Nernst equation, products over reactants raise their stoichiometric coefficients is Q, right, leave solids out of the equilibrium expression. The number of moles of electrons being transferred is 2. Well, 1 squared is 1 divided by 1. The log of 1 is 0. 0 times anything is 0. So what we get when we're at standard conditions is that the voltage at non-standard conditions is equal to the voltage at standard conditions, right? This is where we're at in terms of the equilibrium. So the voltage at this point, right, during the process is 1.24 volts. Okay. So if I change these concentrations, right, I have a 10 molar concentration of the silver concentration, right? That's more like, right, with the 10 molar concentration of the silver, we're more like we're starting with a fresh battery, right? We're starting with a high concentration of reactants and not such a high concentration of the products, right? The ratio before was, equal, right? 1 molar concentration of iron 2 plus, 1 molar concentration of silver. Now, we're more towards the beginning of the reaction. So the expectation is the voltage of the battery is going to be higher. So when I plug this value in, these values into the Nernst equation and solve, I end up with a voltage that's higher than standard conditions, right? It's more like a fresh battery. I'm starting more at the beginning of the reaction. So again, what we're doing with electrolytic cell is separating the reactants, right? The solid iron that's giving up its electrons is separated from the silver that's taking the electrons by a wire. And we're making the voltage, right, go through a wire. All right, and this way we can do work, electrical work.